Namaste everybody, namaskar, welcome to the next lecture in linear algebra for using geometry. Uh, Remember that we did in the last class, we were actually trying to work out the difference between points and vectors, and we looked at what happens to points. We said that these are fixed coordinate fellows, whereas the vectors are basically they are frame independent or they are coordinate independent, and then we looked at certain interesting properties of points and vectors. We also looked at the notion of let us say the idea of orthogonality and stuff. We also looked at the idea of unit vectors and all those things. In this lecture that we are going to have, we are going to look at how do we combine vectors and why do we even need to combine vectors. So, what is the what is the reason why we want to combine vectors and how do we combine vectors? We will look at that. We will ask this question, can we actually combine points? If we are not able to combine points, then we will ask, like, can we combine vectors as such? Then we look at the combinations of vectors, what does it yield and where do we see these combinations of vectors and stuff. And at the same time we will also look at the idea of angle between vectors. What is it to say, what is the angle between two vectors that you have, and are they orthogonal or are they along the same direction, or if they are in different directions, so what is the angle between them. We will look at that, and we will also look at what we call as the orthogonal projections. So, that is the agenda for the class. So, let us get on to the class. So, in the last class we actually stopped in the last lecture, we stopped when we asked this question, how do we combine vectors, what we call as the linear combinations of vectors. So, the question was how do we combine vectors, and this is exactly where we said we will finish the class, and in this lecture we will look at what is it to say combining the vectors. Okay. Now, so but before going into this, let us look at the idea of let us look at combining points. Okay. Recall, we did in the previous case, recall that adding vectors or scaling vectors was completely different. Scaling vectors was completely different from the operations that we do on points. The reason is the points had a fixed coordinate and therefore they depended on the coordinate system that you are using, or what is the kind of origin and reference points that we use. So, it was completely different from adding or scaling a point. We really do not even know what it is to say scaling a point. Let us probably not worry about it for some time now, adding or scaling a point. However, what we know is, we really know this, adding 2 points, we said that adding points was a coordinate dependent operation. I hope we recollect what is it to say coordinate dependent operations. If you shift the coordinates, then the values change. So, these are all basically coordinate dependent operations. However, we ended up doing this. So, what did we do? We basically took a point P, let us say here, whose coordinates are given by let us say P1, P2, and we wanted to move to another point Q. Let us say this is the point Q, and we had this point to be let us say Q1, Q2, and we said that you go along the direction of this vector V. So, what we did, we basically took this point P and we added that vector V, and we ended up getting this point Q, right, or rather we said that Q minus P was actually giving me the vector V, which was basically let us say Q1 Q2 minus P1 P2, which gave me let us say q1 minus p1, q2 minus p2. This is what we had, right. That means what we figured out was we could add a vector to, let us say we can add a vector. So, we add a vector to a point and that operation was allowed. We add a vector v to the point P, to basically reach the point Q, right. That was something known. So, now let us define something interesting. So, let us define a new point R, let R be a new point which is defined as follows. Remember, we can scale vectors. Scaling a point does not actually make sense. So, what we do is we scale vectors. So, what we are going to do is we are going to take up this, we are going to say look, probably we are going to say R is equal to P plus half times V. That means you are going to scale the vector V by half, right. This is basically the scaled version of the vector V. And what is the scaled version of vector V? That is pretty easy to know, because V was obtained as Q minus P, right, the difference between the 2 points that we had. So, this is going to be equal to P minus P by 2 plus Q by 2. So, we are going to have, this is nothing but P by 2 plus Q by 2, which is basically giving me P plus Q by 2, and which is actually half of P plus Q. And what is half of P plus Q? And that is something which we all know, that is basically the midpoint of the line segment, joining P and Q. That is pretty interesting, because we said that we cannot adding 2 points was a coordinate dependent operation, we said, and we also got into another what do you call situation, where in which we added 2 points and scaled it by half, and we ended up getting another point on the line which connects the 2 points. So, midpoint of the line joining the points P and Q. Joining the points, let us say P and Q. For example, let us take this up, let us take an example. Suppose I take P is equal to this point 1 4, and let me take this point Q, which is 3 6. So, the midpoint R is basically given by half of P plus Q, which is basically 1 plus 3 by 2 and 4 plus 6 by 2, which is 2 comma 5. So, what is interesting to see is the following. So, thus we see that R is equal to, let us take the point P plus some k times V, where k is basically a scalar, k times V, and that I can write this as P plus k times I can write this as Q minus P, which is nothing but 1 minus k into P plus k times Q, right. So, what we are going to say is, if the so what we are going to make a nice interesting inference out here, and what is the inference? We say that this point R, which is given by 1 minus k times P plus k Q, is always a point on the line segment, on the line joining is always a point on the line through P and Q. P and Q, right. We can actually change the different values for K and then check it. It's easy to verify that the point I mean R, which is given by 1 minus K times P plus KQ, is always like a point on the line connecting the lines connecting the points P and Q, right. So the factors K, the values K and 1 minus K, these are called as the coefficients, right. Okay. So we are going to make a nice definition here. What happens if the coefficients add to 1, and we will see where we land up in such a situation. So we are going to say definition, a weighted sum of points where the weights add to 1, a weighted sum of points, where the coefficients sum to 1, you have a name for this. We call this as the barycentric combination. In fact, what is interesting is when we write R is equal to 1 minus K into P plus KQ, you also see that this allows to construct R anywhere on the line defined by P and Q. Typically we try to do what is known as the linear interpolation. So this is basically some idea of linear interpolation. So let us make another definition here. We are going to say that if 0 less than or equal to K less than or equal to 1, there is a name for this. We call this combination as a convex combination. This is something which most of us study when we do optimization and convex optimization and stuff, where we have a form like this. We call this combination as the convex combination, as convex combination. Oh, very good example for this is basically the example average of two numbers, that gives the center of gravity of 2 points. Anybody who does random variables, you will see that expected value of x is basically given by sigma x into px of x, where px of x is the probability mass. That corresponds to the weights, and the values that you have are basically the values the random number can take. So you see that there is a convex combination happening over there, right. So if you want to define points outside of the line segment PQ, then you need to take K is less than 0 or K is greater than 1. So to define points outside the line segment, PQ, choose K is less than 0 or K greater than 1. So that will help us get the points which are outside the line segment. That means you have this point P and you have this point Q. Suppose if K is between 0 and 1, you end up getting all the values out here. If the value is between k and k less 0 less than or equal to k less than or equal to 1, you get values here. Anything beyond is basically you, if you want to get points here and here, you choose k appropriately. Is that okay? It's k less than 0 or k greater than 1, you choose it appropriately. Okay. You can also have barycentric combination of more than 2 points. So you say k1p plus k2q plus 1 minus k1 minus k2 into r, so you can even do that. Now what we do is we said that points cannot be combined, but then we also figured out that there is a sensible way of combining points where we ended up getting the midpoint of 2 points which is lying on the line segment joining the 2 points p and q. Now what we want to do is we want to look at the idea of combining vectors, right. So what is it to say combining vectors? So we are going to look at combining vectors. So what is it to say combining vectors? Suppose we already have, let us say I mean we are going to discuss only 2 component vectors for now. So let us assume that let u and v be two component vectors, that means they are there on the x1 x2 plane, 2 component vectors such that the vector u is given by u1 u2 and the vector v is given by v1 v2. Probably I mean we use this sign, I mean the notation with the arrowhead. You can do that. In fact, even the previous topics whatever we have done, we could actually use the same notion of having an arrowhead, or you could use a underscore v which could actually make the notation very clear. So okay. So this I have u is a vector and v is another vector. So what is it to combine the vectors? So I am going to look at what is u plus v. U plus v is nothing but u1 u2, the 2 components of the vector, just write it down and you write v1 v2. Now what do we get? U plus v is nothing but these 2 are real numbers, u1 v1 are real numbers, u2 v2 are real numbers. Just do a component wise addition. So u1 plus v1 u2 plus v2, and interestingly what we see is that even this is equal to say another vector w which is given by w1 w2, where w1 is where w1 is equal to u1 plus v1 and w2 is u2 plus v2, right. We can actually do a scalar multiplication of the 2 vectors and then we can even add, right. We can do the same thing. So what we see is this w is also another vector, is another vector which we call as the resultant of the 2 vectors u and v, another vector which is basically the resultant of u and v, right. Similarly we can actually do the scaling business. So for some real scalars, so let us assume that for some real scalars, real valued scalars, say for some real valued scalars, let us say alpha 1 and alpha 2, we can write alpha 1 u plus alpha 2 v is nothing but alpha 1 into u1 u2 plus alpha 2 into v1 v2, and that is going to give me alpha 1 u1 plus alpha 2 v1 alpha 1 u2 plus alpha 2 v2, which is yet another vector is what we see. And so this is, let us say, let us call this vector as, let us say the vector z. The vector z is going to be alpha 1 u1 plus alpha 1 u1 plus alpha 2 v1 alpha 1 u2 plus alpha 2 v2. So, what we see is z is also another vector. So, z is given by alpha 1 u plus alpha 2 v. We say that z is obtained as a linear combination of the two vectors alpha 1, I mean of the vector u and v. Okay. So, we say that linear combination of u and v. Is that okay? So, what is it to say linear? Let's see geometrically what it actually means. That makes a bit more I mean the understanding a bit more clear. So, I am going to have, let us say, the vector, let me mark those points, this is x1 axis and that is x2 axis. So, let me mark points this way. So, 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. So, I am going to take the vector u to be equal to, let us say, 1, 2 and v is equal to this vector, let us say 2, 3, right. So, the vector 1, 2 is going to be here. So, let us mark it this way, this is the vector u and the vector 2, 3. Okay, let me make the change a little bit because we can clearly put this. Let me make this as 3, 2, 3, 2. So, the vector 3, 2 is going to be here. So, let me draw that vector. So, this is going to be the case. Now, what is it we say? We say that w is equal to u plus v, which is nothing but 1, 2 plus 3, 2, which is nothing but 4, 4. And where does 4, 4 where is 4, 4 located? 4, 4 is somewhere here. So, this is 4, 4, right. And we already saw I think in the previous class where we basically, okay, let us try to construct a parallelogram here. So, this goes here and you draw that in parallel. So, this is the point that we get, which is this is the vector w. Is that okay? So, that makes a lot of sense. Now, you can scale the vectors, you could probably do some scaling factors. Say suppose I take alpha 1 is equal to 3 and alpha 2 is equal to, let us say, minus 1. So, I have z vector to be equal to alpha 1 into u vector plus alpha 2 into v vector, which is 3 into 1, 2 plus minus 1 into 3, 2. That is interesting. I am going to get a vector which is 3 minus 3 and this is 6 minus 2. So, I am going to get a vector which is 0, 4 and that lies on your x2 axis, right. So, that is going to be the combination. So, now what we are going to look at is something interesting that happens here. Say suppose, let us assume that suppose if u is equal to 1, 2 and v is equal to 2, 4, what happens to u plus v? What happens to the vector w, or instead of saying what happens, let us say what is the vector u plus v? What is w is equal to u plus v? So, what is that going to be? We say that the w vector is basically 1, 2 plus 2, 4, which is 3, 6. Interestingly, if you look at the, if you plot these vectors, if you draw these vectors and then see how does this, the vector u, the vector v and the vector w look, it is pretty interesting. Let us do that. 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So, let me take this as again x1 axis, let me take this as x2 axis, 0, 1, 2, 3, 4 5 6 7, 1 2 3 4 5 6 and 7. Let us again draw those two vectors. 1 2 vector is basically here and 2 4 vector. It is interesting to see that the 2 4 vector is also along the same direction. And what is even more interesting is you see that the vector 3 6 is also along the same direction. All these vectors u, v, w are all in the same directions. However, if I take let us say w is equal to the other one that I had, where I had 1 2 and no sorry not w, u is equal to 1 2 and v is equal to let us say 3 2, w was 4 4 and what we figured out was 1 2 was in a different direction, which you could see from here. The vector 1 2 is in this direction, this is the vector 1 2 and this is the vector 3 2 which was in a different direction. Now we could see that there is a parallelogram that is formed out of the two vectors u and v. That means the vectors u and v are the two adjacent sides of a parallelogram, they form the two adjacent sides of the parallelogram and this parallelogram encloses a certain area, right. And what we see here, if you look at 1 2 2 4, we see that all the vectors are along the same direction. If I take this to be the vector u, let us take this to be the vector u and let us take that vector to be v and let us take that vector to be w. We say that all of them are in the same direction and there is no parallelogram that is formed. Now what is it that we get out of this? I mean, why are we even worried about this parallelogram stuff? What is interesting is if in 2D that means I have only vectors which are two component vectors. Suppose u and v are two vectors that are in the same direction. Now what do we mean by the same direction? We will just look at that are in the same direction. I would say they are parallel to each other. So that are in the same direction, in which case we are going to say u is equal to say some alpha times v and this is going to be two vectors which are in the same direction. We call u and v to be as linearly dependent vectors. Of course, we will see a very formal definition in the subsequent topics to come. When we look at vector spaces and stuff, we look at more formal definition of linearly dependent vectors and linearly independent vectors. So we will say that these are linearly dependent vectors. If they are not, if u is not equal to alpha v for some scalar, alpha is some scalar, for some scalar alpha, we say that u and v are linearly independent. That means independent. Now what does that mean? Linearly independent vectors, in this case two linearly independent vectors in R2, oh I should not sorry in 2 dimension, let me say in 2D, enclose okay let me do this. If two vectors are linearly independent, in 2D, we say that the parallelogram formed encloses a certain area. Formed encloses an area. And what is that area? We will see again. We will see that if you put these two vectors as the two columns of a 2 by 2 matrix, we see that the area of the parallelogram is basically given by the determinant of the matrix. We will do a proof for that. So, if the vectors are linearly dependent, then there is no parallelogram formed. If the vectors are dependent, then no parallelogram is formed, and therefore area enclosed is 0. That means the parallelogram basically degenerates to a line is formed, area is equal to 0. Now, what is the use of this two linearly independent vectors? Why are we so interested in linearly independent vectors? If the vectors are linearly independent in 2D, if the vectors are linearly independent in 2D, we can reach any destination on 2D in 2D, any destination in 2D that is, we can obtain every vector in 2D as a linear combination of these linearly independent vectors. We can obtain every vector in 2D as a linear combination of these linearly independent vectors, combination of the linearly independent vectors. That means we are going to say any vector W can be obtained as alpha 1 u plus alpha 2 v for alpha 1 alpha 2 scalars and u and v linearly independent vectors. So, what we do now is having seen this, we just want to see I mean we want to look at certain examples of this linearly independent vectors, and how does this idea of linear combination take me to different I mean help me get different vectors as linear combination of these two linearly independent vectors is something which we will see in the next lecture.